Well, it's the usual time. Welcome back, everyone. And happy Wednesday. We're midway through week number 13. And this is our standard wrap up of the announcements. We're on the last example of Unit 8B. This one's kind of tricky because we're using the calculator, using the log function, and it's an even trickier one with all those negative signs thrown into the mix. But after we move through that, we'll be in our pretty much the penultimate section or unit of the entire semester. With what we have going on next week, we'll be reviewing Thursday, so that we'll be reviewing ahead of our exam on the 20th of next week. That's week number 14. Then we'll be doing our last two sections of new content on the 22nd, the 23rd. We might be wrapping up topics then on the 27th. That's now on week 15. But then we'll be very shortly going into review mode for the final exam on Monday of that day itself. And so the rest of the week here on week number 15 is just reviewing for the upcoming final exam. So we're nearly there. We just have another formality, exam 3, to get through. This one is pretty focused on just chapter 5, so it makes it a less kind of strange exam with random topics. This is pretty unified. As normal, best way to start thinking about putting together your formula sheet is start reviewing the problems on the quizzes to get caught up, the homework assignments on MyLab rather, and then also double check the formula sheet here. This is just a container of lots of definitions that you don't have to duplicate when you go to write your formula sheet. For next class, like we mentioned, we'll be reviewing for exam 3, but any questions about it at the moment? Okay, well, it won't be too long of an exam. Again, I can't ask everything that's on version 1 or version 2 of these notes. Version 1 is the actual lecture notes as worksheets, and version 2 is just brand new, fresh problems. So we'll probably spend some time going over some of these problems here for our upcoming review on tomorrow's class. For now, so that we're getting through our chapter 8, we're going to go back to Unit 8B, working on a little bit more on half-life and exponential growth. Then the next unit feels like it's got kind of a good amount of carryover, but the topics are new, just not at first. There's a good amount of review just to start out in this unit. But here's finally where we left off on Monday's class. We did a computation on this one. We actually put into the calculator, got a value out. But we kind of emphasized that we want to go a little bit slow on this one because it is trickier than it seems to get this done just right. So we'll practice this one on 2 different calculators. Well, really 3 different calculators, the TI-30X2S. We'll show how it goes on the TI-30XA. If you have your calculator you intend to bring to the exam by you right now, that's good to pull it out and check the work as we go through this one. One thing we did first is, for this particular problem, we want to use the exact half-life formula. So that's why we're going to take our time doing this computation here. But this is a good strategy for a quiz problem. Well, I guess I didn't ask this question on the quiz. This is a good strategy for, say, a MyLab problem or a problem on the final exam if this question comes up. If you do the approximate time, then that's a pretty good check because our answer should be really close to that value there. If the decay rate is 0.002876, then we take that, drop the percent symbol, take 70, divide by that number, and that should give us a decent half-life time. But now we want to do it exactly, so we're going to focus on this formula here. Well, that's a recap so far, but let's refresh on the context. We're looking into the Onkalo Spent Nuclear Fuel Repository in that location in Finland. They are sealing away 65 metric tons of plutonium-239, and that particular isotope of plutonium has a decay rate of 0.002876% per year. So an extremely stable isotope of plutonium. So that's our R value. What we did here is we converted it to a decimal. That's the first tricky part about this exact formula. R is now as a decimal, so we took this, divided it by 100. Or better said, the decimal point is by the red dot. We just shifted 2 spots to the left. So now let's throw this into the calculator, see what we get out. Any questions whatsoever with the recap before we start to compute? Hang on, I got one small problem. I usually have a drawing pen somewhere up here. Let me close Word and reopen it to try to get my drawing controls back in. One small hang up here. Should probably save that. I thought I was all ready to go, but sometimes you never know until you find the first problem that occurs. And yeah, it doesn't show my drawing tools. Probably can freehand it or type it out, but let me see if I can get this working. We'll make this work one way or another. It could be my writing tablet that's a problem. Let me close this. Probably close both Word files just in case one's bothering the other. All right, reconnect. Okay, and now they're back. I don't know what causes that problem, but every now and then, every like 50th class, it glitches out on me like that. Sorry for the distraction here. Let me get my windows about where they were. Okay, I think we can actually start now. So thanks for your patience with that. So back to this problem. First thing I want to do is just put it down on paper. If this comes back as the final exam question, like we mentioned before in a lot of the formulas, I give a massive amount of partial credit to have the exact correct expression on paper, even before you put it into a calculator. So that's like our insurance on the problem. So let's write out carefully, T half for the half-life is negative log base 10 of 2 divide by log base 10 of, here's where the first big confusion of the problem is. The author has to write plus here to make the formula correct, but the decay rate is actually a negative value for R. And so when we go to plug it in, there's in fact a negative sign that goes right here to start it out. So it's going to go 1. Actually, it's a minus right here. Then the author, I think we mentioned before, could have put a minus right here in the formula, but because R is negative, that would have been a double negation, and it actually messes up the formula. It has to be in that form. But once we have that, we put in R as the decimal number, 0.00002876. And because we're going to plug this into a calculator, it's not so bad with this one putting everything in exactly on paper. But it's probably a good strategy for the other calculator to just do this subtraction right here. Let's go 1 minus 0.00002876 and throw that value inside. That's going to make the calculator work a lot nicer to get through. So T half, we're going to take negative log 2. And just to be specific, let's call that log base 10 of 2. We're only using one logarithm, but still it's a good practice to say it that way. If you called it log 2 without the base 10, I wouldn't take off credit, however. The denominator is log base 10 of, citing Desmos up here, let's throw in 0.999971124. Okay, so we are ready to go. On the calculator we see here on the right, if you have a calculator like this or similar to it, the expressions we're going to be using is this button here for the logarithm. We'll be using the parentheses as well. But actually, the thing that's really tricky about this particular problem is that one negative sign right there. It has to be put in differently using specifically that button, that one and only button. So throwing that into the calculator, here's what you should be seeing. And let me know if you're getting something different. We'll explore different ways to compute with this one. So we'll get negative log. On Desmos, log just means log base 10 as a default. So that's all you would have to write. Divide by log 0.99997124. So this comes out as a positive, and we're rounding out to the nearest year, 24,101 years. So that's how long it's going to take just half of the 65 metric tons to decay. So we're long gone, but still, they're trying their best to build a repository to contain the 65 metric tons. There's more of that on the planet. But any questions at all, folks, getting that number? Okay, if you can get that number, just as you see here, MyLab is going to be kind of pain-free. These are the last couple exercises you'll see in MyLab using the exact half-life formula. Then, if you're using the other calculator, here's what the steps would look like for this one here. And there's no harm, once again, like we mentioned before, in just dividing it up. If you looked into just the numerator, negative log of 2, and write down, say, 7 or 8 decimal places of this number, then divide it by log 0.99997124, then probably keep 5 significant digits on this number, meaning keeping lots of decimal places on this one. Dividing by a number really close to 0 can make the error really propagate. So the bad thing about this strategy is you have to carry in a lot of digits to divide it accurately. So if you can get it into this calculator in one shot, it's definitely better than trying to split it up, top versus denominator. So in this calculator, the functions you need are that log key. We're going to need the negative sign, and that's pretty much it. The division key definitely, equality key definitely, but log and the sign interchange button down here are going to be the major ones. So if you have a calculator like this one, give it a try, and you should see these numbers pop up as you're practicing this. First thing you want to do is work in the numerator. Hit the 2. After you have 2, hit the log key. You should see 0.3010299 and some change, but it's positive and it's got to be negative. So you can hit, at this step, the sign interchange key. It just throws a negative in front. So now you should be seeing this in your calculator. After that, immediately hit divide, and then just do it all over again. Type in this number, 0.99997124. After it's in, hit nothing else but the log key, and you should see this number pop out, negative as well. So your TI-30XA has stored both values because division was hit in the middle. Last thing to hit is the equality key, and it comes out to that same figure, rounding to the same 101 years. So definitely a tricky calculator. I usually practice this a couple times before class just to make sure I've got the sequence just right. Work inside out, go top to bottom, and use that to change the sign here to negative. Any questions?
Sorry. Oh, sorry. I think I misheard, but where did the 0.9997124 come from?
Oh, we did that kind of as a middle step, just so that we didn't have to do the parenthesis thing inside this calculator specifically. I took from this step right here.
Oh, I see. Thank you.
Yeah, you bet. And that's, again, big quality of life improvement on this particular calculator. Otherwise, we'd have to use those parentheses keys in the middle. Other questions at the moment? Okay, well, we got it, folks. If they're storing plutonium-239, a high-level nuclear or a nuclear byproduct of things along the lines of, well, where does it say that? I'm trying to use their wording. Well, this is a byproduct of things along the lines of nuclear reactors. So lots of this stuff gets produced, not intentionally to build weapons, but just as a byproduct of trying to generate electricity. So we now have on part B, 65 metric tons of this stuff. It's being thrown into the Onklo spent nuclear fuel repository. This thing's rated to hold plutonium for 250,000 years, 250,000 years. So we want to just wonder if the repository is successful, nothing happens, it doesn't crack open and leak out the plutonium, how much is left in 250,000 years, given that half-life of 24,101 years? So that's a pretty impressive what-if question. And here's how it would go. The good news is we're just reusing these formulas again. We're using the exponential decay. Only thing different in part A is we have the exact half-life, not an approximation. We're going to use new value equals initial value, 1/2 to the power of t divided by t half. Let's cite that as we compute, just for the emphasis on the process. Okay, so there's our formula down below. In using that formula, there's a couple things we still need. We have that part, t half in green. We need the time t, but that's what this part is saying. T equals 250,000. We also need an initial value, but that's going to be the 65 metric tons that gets sealed away in the repository. So this is the initial value. Now that we have both of those all together, we can say the amount left, amount of plutonium, 239, is going to be the initial value. So take 65 metric tons. Unit for that is just a lowercase t. Multiply by this portion right here. This is going to be the fractional decay rate. So 1/2 to the power of t. So we take our 250,000. Divided by the half-life, t half. Let's just hit that with green to emphasize that's the other green part in the formula. 24,101 years. And throwing all that into the calculator will give us a value out. So let's put this in carefully. 65, drop the unit and just go times 1/2. I usually put this whole thing into an entire set of parentheses. Otherwise, the calculator might misinterpret you, thinking you meant just 1 to a power. So then raise that to the power of, now do a division here. Probably another set of parentheses is not a bad idea, just for the sake of emphasizing the calculator, the order of operations here. So 250,000 divided by 24,101 gives us this figure here. We're rounding to 2 decimal places, so this is going to be 0.05 rounding up tons after 250,000 years. So that's our conclusion on that one. Any questions or comments at all, folks, getting through this one? Or any issues with the calculator whatsoever, getting these values in? Okay, well, we got through it. This was a pretty long section of notes with 10 examples, some going really fast, some we took extra time on, the ones that had to deal with logarithms, for example. And then reading in the book and the notes are kind of strange going forward because I noticed in the reading, we built up some pretty impressive formulas, but author doesn't really use them at all in the next section. That's kind of strange and frustrating in a way. But we'll take a look into practicing them again on the MyLab homework assignment for this unit. And I think probably the bigger reason we're looking into logarithms is that we're going to look into more problems involving them when we go into Unit 8D, the last unit of the semester. So let's save this up for now. And next, this is the second to the last unit of the entire semester. So this one has a kind of fancy name. It says real population growth. I mean, we were doing growth in Unit 8A, we were doing growth in Unit 8B. So the author has something really specific in mind when he has this statement, real population growth, as if we weren't doing it the whole time. But it's an appropriate statement, even though it seems kind of strange and bold a statement to make out of nowhere. In this unit, formulas like these just come right back from the prior unit that we're working on. And notice it's the approximate doubling time that we're using all pretty much exclusively in this unit. We're only going to be looking into doubling time because we're looking into growth exclusively rather than decay. So here's how the problems are going to be set up. Examples 1 and 2 are in fact really just kind of review problems, which is strange. But let me show you the tour of the notes to kind of indicate what the real objective is on these notes, not just to redo problems over. When the author talks about real population growth, one thing he's talking about is ways to construct the growth rates of various countries, growth rates of various organisms of animals, and so on, is looking into things along the lines of birth rate, minus death rate, migration rates also can be factored in, and so on. So we'll focus a little bit on this formula here with the idea of thinking about the so-called real population growth. But another big reason our author calls it real population growth is pretty much because of problems like these that we did. This was from Unit 8A, and the idea was someone took a payday loan of $300. The interest rate was strange, fictitiously high, but at 1,200% compounded monthly, implying a doubling time of every single month. And this might be realistic to an extent, in the sense that there are real payday loan companies that go as high as 700% in the USA. Also, this kind of an exponential growth could make sense along the lines of 2, 3, 4 months go by. This kind of formula could be in fact used at a more reasonable interest rate. And we're never going to get to a value like this, where we're in the trillions of dollars. So what's going on with exponential growth is an exponential growth model like this one, or the ones we were just working with in the prior notes, really coming up with these kind of formats like we've seen before. They're plausible over short time frames, but in the very, very long run, these kind of formulas break down in a massive way. In terms of money, there's no way a payday loan could collect in trillions of dollars like this. But also in terms of population size, a population growing like the population of the planet, it does have exponential growth we can assume over short time frames. But the time goes long enough, then the size of the human population is just going to exceed what's available in terms of space and resources on the entire planet. So exponential growth can never continue forever. That's the real takeaway of what the author's talking about when he calls this real population growth. Exponential growth is only realistic over short time frames. So what we're also doing in these notes is looking into the logistic growth model. This one takes into account a population size against the carrying capacity, how much the environment can even support in the first place. And this gives us a model that's actually far more realistic, something that can actually be used in the long term and very successfully modeling populations, whether they're bacteria, animals, or humans in a country or on the planet. So this is the ultimate target, but we're going to review just a couple concepts to start out on the first couple examples. I felt like that was a good kind of introduction because if you look at what we're doing here, it feels like it's just the same unit, but it starts to change gears pretty fast. Think of this as just a couple refresher problems from the last unit. Well, any questions at all, folks, before we start cracking open this unit in earnest? Okay, well, I have a couple examples that are once again kind of warm-up problems. These were problems that were done in this book. Same kind of problems you'll see again in MyLab. The lecture notes are always pretty parallel to the MyLab exercises to help out. So we have a restatement of the approximate doubling time formula. It says if a quantity is growing exponentially at a rate p%, for this formula, like we've discussed before, drop the percent symbol and take 70 divided by p, the rule of 70. So if we apply it to this kind of problem, then the p for this one is going to be 2.5. It says here in the year 2000, the population in Nigeria was about 122 million, and it had an annual growth rate of around 2.5%. So if that continues to go forward into the future, from 2000 to the present to 2060, if nothing ever changes, we can find out the doubling time and make a projection of the population size of Nigeria in the year 2060. First thing, we're going to use the approximate doubling time. Like I mentioned before in the prior unit, I'll always try to be very, very specific which doubling time we're using. If it's the exact doubling time, I'll probably put it in bold or something like that, just as an extra hint that we're not using this formula here. We'll round it to one decimal place, and it goes pretty fast. Just take t double. It's going to be 70 divided by 2.5. So that's the p value that goes there, and we get as a result. I think we've done a similar computation. I have deja vu on this one for some reason. 70 divided by 2.5 comes out as 28 years. I think 2.5 must have came up on a prior unit, the last unit maybe. But that's what it's saying so far. The population is 122 million in year 2000. Then in the year 2028, it should have 244 million and so on, is what this approximation is telling us. Let me put my approximation symbol there. Just as a reminder, it's a legitimate approximation. Any questions at all, folks, with the doubling time? Okay, and I made an edit right here. It originally said round to the nearest person, which is an appropriate thing to do, but I felt like that became kind of tedious, busy work. Because if the problem is giving 122 million, it makes more sense just to round to the nearest millions. So that's the reason for that change there. Sorry for the random edits on rounding. Here we need to cite a formula that's going to go new value equals the initial value times 2 to the power of t divided by t double. So that's our formula to use. It needs two values, the so-called initial value and a time. So again, we have to be kind of careful with these. I think this kind of context has come up before. If it says, what is the approximate population in the year 2060? An easy mistake to make, really, is to put 2060 right here. But what we're using is the amount of time since the year 2000. So what we're really doing is saying, if we have an initial value of 122 million, and it's based in the year 2000, that means time itself, the t variable in this formula, is going to be 2060 from here minus 2000. So we're really finding the population after 60 years have gone by, since the 122 million is based on the year 2000. So T equals 60 years. We want to know the approximate population in the year 2000, meaning we need the initial value. Since T is 60 years, we're going to use the 122 million that belongs to the year 2000 figure. So this will be initial value equals 122 million. Well, that's our setup so far. At this stage, again, it's a pretty legitimate review problem. All we're doing is plugging in values. So we can now say, in place of new value, we can leave it described as new value, but I'll call it population of Nigeria is going to be equal to now, take initial value, the initial population size in the year 2000, our base year, 122 million. We multiply that against 2 to the power of 60 years divided by the doubling time, doubling every 28 years. And pretty similar to what we did in the last problem, except this was a 1/2, and we had a half-life where the 28 is right now. So that's our setup so far. All we have to do is jam it into the calculator. Any questions at all, folks, with the process or the setup? Okay, back to the calculator. And let me know if you have any issues with the calculator on these problems. It's not as extreme as dealing with the double logarithms and negative signs and all that, but if you have any issues on getting the same value, let me know at any time. I'll be happy to look into it further. Let's take 122 times 2 to the power, 60 divided by 28. And that gives us this figure here. We're rounding to the nearest million of people. So this would round up to 539 million. So this equals 539 million people in 2060. So in the year 2060, they've exceeded the population of the USA by a lot, but for the 2025 value. The USA is also growing, so we would have to see how far each country gets by 2060 to make a better comparison. But we did it. That's the conclusion to this whole problem here. And in this section notes, we're not going to ask for specifically things like by what factors it's increasing by. That was more of the last unit. It's going to always be using this formula here for the follow-up question right after. Well, I guess another reason we can call this real population growth is we're looking at real populations, realistic historical values. We'll be doing the same with the next example. Any questions at the moment before we try out a fresh one? Okay, well, we're on our way with these notes. Here's the next example. Probably should be pushed to another page. Let's not try to cram it in. And this one's kind of interesting because this one is a really massive comeback story for a particular organism. It said, before the 1700s, there was an estimated 16,000 to 20,000 southern sea otters that thrived along the California coast. Goes on to say, unlike other marine mammals, these otters rely on their incredibly thick fur to keep them warm. And the fun fact is that they possess the thickest fur of any mammal with up to 1 million hairs per square inch on their body. So this is a pretty extreme animal, in fact. And that made them a massive target, is what it says next on the context. This is the unfortunate part. They became a massive target during the maritime fur trade. And by the early 1900s, they were hunted so ruthlessly that they were believed to be just utterly extinct in California. So this is where the comeback story comes in. There was a discovery in 1938, so almost 100 years ago, of a tiny hidden colony of about 50 surviving otters discovered tucked away in the remote coves of Big Sur, California. that's a real place. Let's take a look at it just to get a good feel of the context. So randomly, someone went across one of these coasts and they just found a cove that had 50 survivors of an organism that was thought to be extinct for probably about a half a decade, close to at that time. So that's a pretty shocking discovery. And since that time, they've been trying to revitalize this once thought extinct species of otter. And we're told that every single southern sea otter alive today is a descendant of that group of 50 survivors that they found in Big Sur, California. Now, currently in the year 2025, the annual growth rate of that southern sea otter, it's a modest 1.5% approximately. So that's the context so far. We're looking into a species of sea otters that are coming back from a population size of 50, but we need to be really careful with this context. That 50, much like we're the last problem with Nigeria, that's not necessarily going to be an initial value in the problem, because we're looking into the 2025 population size. Currently, well, based on 2025 data, it's at about 3,000 otters. So it's not growing extremely rapidly, but it's growing. First thing we want to know, thinking about the growth of this population, revitalizing the southern sea otter, is what is its approximate doubling time if it's growing at that rate. So again, kind of a redo of the last problem that we just did, just a different context, slightly different numbers. But contexts like these, where you're reading through a couple paragraphs, it's easy to kind of lose our way. So it's easy to accidentally flag this as an initial value in the year 1938, but the problem has a different initial value that we're going to use. For the doubling time, the only figure we needed really was that right there. That tells us that P in the formula is going to be 1.5. And our approximate doubling time formula, what it's indicating here, is going to be T double is approximately 70 divided by 1.5. So now we're ready for the calculator on this one, rounding it to one decimal place. 70 divided by 1.5 comes out to 46.7 years. So quite a lot of time, almost at 50 years, half a decade, for the population size to double. And that's telling us a lot about that. If there was 50 discovered in 1938, and in 2025, there's currently 3,000 otters, it probably also means that the growth rate was higher for a while, but it's actually slowed down for reasons that, or it could be lots of reasons, other predators, maybe other natural things happening, maybe shipping, all sorts of things. That California is a busy place, for example, could be limiting the growth rate. It looks like it's slowed down to this value for 2025. So if it stays at 1.5%, we can still make a projection of what the population size will be in the year 2040. Well, any questions with the problem so far? Okay, we're about to reuse that last formula that we did on the first example. So to get to predict the population in 2024, again, it's easy to kind of lose our way in the context. There's a lot of numbers. There's 1700s, 1900s comes up, 1938 comes up. But part B is specifically asking us to predict the population in the year 2040 based off a 2025 figure with an initial value of 3,000 otters. So that context in part B is specifically telling us that T is going to be 2040 minus 2025, which means the amount of time T in the formula is just going to be 15 years. From that, we're going to just reuse the formula that we had right above here. New value equals initial value 2 to the power of T over T double, by just using these new values we see here. So we can say now number of otters. It's going to be the initial amount, 3,000, the amount initially in 2025 is how we're considering this, not the original 50 survivors, which makes sense because, again, the growth rate in 1938 was probably quite a bit different than 2025. So we're using this figure, 3,000, multiply that against 2 to the power of a time t, 15 years, divided by the doubling time, 46.7 years. We often write that in with just units automatically canceled because they will guaranteed cancel out. And if they don't cancel, we need to make a unit change on that to get the right values. So let's plug this into the calculator one more time, and then we'll be on to some different kind of content. This is the end of the kind of refresher review portion of these notes. So 3,000 times 2 to the power 15 over 46.7 gives us altogether, rounding to the nearest otter, we have a projected amount of 3,748. Again, not a lot, but better than nothing, right? 3,748 otters in year 2040 is our projection. Something could change. We could possibly find out why their growth is so limited. Again, it's possibly predators, pesticides, maybe something with their natural food supply is being affected. If that could be solved, then this value might change, and 2040 could look a lot different. Maybe they actually get back to this original amount, around 16,000 to 20,000. That was possibly the original carrying capacity of the species before they were brutally hunted back in the 1700s. Well, any questions at all, folks, running through this problem here? Okay, well, when you try out these problems in the MyLab homework for Unit 8C, again, it's kind of jarring, the whiplash we've had with the formulas so far. We did exact doubling time, exact half-life using logarithms, but the instructions in this particular MyLab section is asking for approximate doubling time. So we go back to these formulas we were using all along to start off the last unit's nodes. Now, again, what we're going to do next is think a little bit more about these growth rates, what gets involved, and looking into human populations specifically. And then we'll talk a little bit more about carrying capacity in the logistic model next. So here's our next big definition. I think these problems are particularly kind of tricky in a certain way. So we're going to take our time with these just to see how they go. There's a couple problems similar to these that we're going to be dealing with in the MyLab homework system. And our definition is nothing entirely new. We've looked at net things like, say, net income on a monthly basis when we were budgeting. Income minus expenses was our net cash flow on a monthly basis. And along similar lines, we're looking into net growth rate. The net growth rate is going to be defined as specifically the birth rate minus the death rate. It leaves a lot unaccounted for, but this is a good way to start talking about how the growth rate of a population is defined. Starts off with this kind of information here. But the United States is tricky if we're being really honest about this kind of problem. The following table gives birth rates and death rates for the United States in 3 different years, the 80s, 1995, and almost 2020. So we have birth rates and death rates, so we're going to analyze, and we're going to use that to think about how the country's population will change in the next 20 years. So we're making a projection based off this tabular data that we have here. But here's the part where it's a little bit trickier than everything you see here on paper. As far as the United States is concerned, the growth rate of the population is not just the birth rate minus the death rate, it's also the migration rate. People coming into the country, people leaving the country is probably just as big, if not a bigger deal than the birth rate minus the death rate. So here we're looking at a limited slice of information and still just making a determination on the best we can on the data that we have here, no migration data whatsoever. Okay, that's the statement of the problem so far. Any questions or comments before we give it a try? Okay, other thing that's tricky about this problem is we have tabular data. We have 6 cells of data, but also headers, column with different information given. And we have to find the net growth rate among 3 different years. So a good way to do this problem is really to just kind of organize. It's easier in MyLab because they give you a table and you just see little boxes you put the numbers in. Slightly harder like this, where you're just staring at white space and you have to get started. So here's a decent way to start off with a problem like this one. If it comes up as a quiz or exam, this is probably about what I would do. I would write down, let's see, thinking about that table, what would I do? Let's go net growth rate. Per 1,000. I did that in a weird way already. I want to column to the left, actually, just trying to visualize what my table is even going to look like. My column to the left is going to be year. And we're going to do a computation for the year 1980, 1995, and 2019. So our growth rate is per 1,000. And here, all we're really doing is working this formula directly. So the year 1980, we're going to take the birth rate of 15.5. People, remember the unit is per 1,000, minus the death rate of 8.7. Throw it into a calculator, we have 15.5 minus 8.7, a net growth rate of 6.8. Which means it's really, again, speaking of the unit, it's 6.8 per 1,000, but we would just leave it on this format. We've already said per 1,000 once in the table. This is a growth rate, but it doesn't mean that the USA was growing at a rate of 6.8% in terms of just birth rate and the death rate alone. Because if you take 6.8, we have an increase of 6.8 people per 1,000 people, means literally divide by 1,000. And if you want this as a percentage, you'd have to go times 100. And in terms of purely just birth rate minus death rate, the growth rate of the population of USA is 0.68%. So that's what this information is telling us in the table. We're focusing on this number before converting it into a percentage. But just for the sake of thinking in terms of what we've done before, that 6.8 is really 6.8 divided by 1,000 times 100%, which is 0.68%. That's a pretty small growth rate altogether. Yet the USA population keeps on growing and growing and growing. But that's because we're also have migration as being a humongous factor as well. Again, 6.8% is tiny because this was a small growth rate just for those otters with a doubling time of 46.7 years. If our growth rate in 1980 was 0.68%, then our doubling time would have been 70 divided by 0.68. You'd be well over 102 years, about 103 years altogether. That's not quite what's really happening with the USA population whatsoever. So once again, there's more going on with the true net growth rate of USA. We're just looking into just one single factor. Well, any questions at all, folks, with the first value? Okay, well, we move over to 15 years later, 1995. That was a good year. In 1995, birth rate is pretty stable from 1980 values. The death rate, it went down a little bit, but it's pretty stable as well. The birth rate fell a little bit more. So net growth rate in 1995 is going to be, using these values, 15.1, minus 8.6. And so this comes out as oh, sorry, I didn't mean to hit, that's the full screen button. 15.1 minus 8.6, 6.5%, or excuse me, 6.5 per 1,000. Again, that's really 0.65%. So the country was growing in that year at the rate of 6.5 people per 1,000. Seems weird to say 6.5, 6.8, but it's appropriate because we're talking about a type of average, a rate really, per every 1,000 people. Then we do it again from 1995 to quite a few years later, now 2019. A lot's changed. The birth rate has fallen substantially. This is a significant change. It was stable in these two reference years here, but now it's dropped to 11.0, and the death rate has gone up. That's really unfortunate. And that's a topic of a huge amount of study already. Why is the death rate going up in the USA? Echo says some of the kids were still being grown. Yeah, that's a great way to think of that. At the 0.5, it's like the meiosis was still happening or something along those lines. But yeah, the data for the USA is kind of shocking when you get to 2019. It makes us wonder what happens in, say, if this table extended to 2026 or 2030. But going as far as to 2019, right when the COVID-19 virus was hitting, our net growth rate was 11.0. Minus 9, really don't need a calculator for that. That was 2. Which means if you converted that to a percentage, like we did before, just to get further context on what is this saying, the population was increasing at a rate of roughly 2 people per 1,000 to over 1,000. Now times 100 is making it a percent. Growth rate is close to 0 at this point. Again, in terms of just birth minus the mortality. So if you take the rule of 70, divide by 0.2, tells us the population doubling time is 350 years, but we're not growing at that rate whatsoever. Our population is increasing much more strongly than that as a doubling time. Well, here we have it. Looking into one factor, birth minus mortality. These are the net growth rates of the USA across these 3 different time frames. Any questions whatsoever, folks, with information we just generated here? Okay, next, part B is a really, really open-ended question. Predict how the country's population will change in the next 20 years. In my lab, it's easier because it's multiple choice. So I'm going to go for an answer that's kind of similar to the ones that you were going to see there in my lab. But if this was an exam question and you said anything that's correct based on the information given here, it's an acceptable answer. It's very open-ended. Here's one way to think about the problem, though. We've seen this kind of situation before. Sure, this is 6.8, 6.5, and 2 per the 1,000 people. But you can turn them into percentages if you really wanted to, like we were emphasizing here in orange. And so the recap problem for this situation is back in the statistics section. This was a different kind of context. We were looking at the CPI value. But even though it's a big bar chart, it was the same kind of idea. We were looking at the literal percent change on this one. Our problem can be thought of as a percent change across these different reference years. And it was a confusing table for sure when we were looking into this. We made statements along the lines of, in which year was the CPI value the highest? We said 2025 had the highest CPI value because the growth rates were all positive as percentages, which meant CPI just kept going up and up and up. It's the same kind of story here. In terms of these net growth rates, if we're thinking 1980 to 1995 to 2019, the highest population is in 2019. Because the growth rates are all positive, it keeps on going up and up and up. But now, thinking about that, how the population is always increasing by a meager amount here, 2 per the 1,000 in 2019, The question is, predict how the country's population will change in the next 20 years. That's a tough prediction because notice how the net growth rate just plummets in 2019. So if you had a different take than what I might put down here on paper, your take could be that in 20 years, this is going negative. It's a prediction, so it's a completely fine way to go on this one. It might be reasonable. Let's maybe go that direction. But if you had a different take, if you said it's decreasing, getting closer to zero, but you're predicting, again, it's a subjective answer, a prediction you're making, and no one has a crystal ball that knows the future. But if you're predicting it's getting close to zero, but never goes negative, then the country's population is increasing in the next 20 years, just not by a lot. So it's open-ended. There's multiple directions to go. Depends on what prediction you're going to make. But based on this drop here that we see, and again, focusing on one factor, that's the unfair part of the problem. Here's what I would say on this problem. Since the net growth rate is plummeting, and maybe that's not completely fair because that's just 1 year of a big decrease. Another data value here would give us more evidence, right? But still, we're just making a prediction. So let's emphasize, I'm predicting that the net growth rate is plummeting and it will continue to plummet. And since the net growth rate is plummeting, we predict it will be negative in the next 20 years, which means the population change would have gone from exponential growth, it's growing here, to in 20 years, it's going to be negative, and we're looking at exponential decay. The population of USA is decaying exponentially in the next 20 years. Assuming, or I didn't finish that thought. We predict it will be negative in the next 20 years. By it, I mean the net growth rate. And so the population will decrease in the next 20 years. So emphasizing we're going to get a negative value in the next 20 years and that the population is going to decrease, that's much like what happened in 2019. The moment a percent or growth rate of amount of people per 1,000, either kind of value, the moment it goes negative, means something is actually decreasing. And this is the one and only year in our CPI table that the CPI actually went down. Did we say anything about that? Yeah, in 2009, the CPI actually went down from the 2008 value. So that's essentially what I'm saying here on this problem. I'm predicting the growth rate will go negative in terms of births and deaths. And so the population of the USA, its size will go down as well. Well, that's one take. Again, you might say that stabilizes around 2 or gets close to 0 but stays positive. You would say then the population will increase, but maybe you'll say increase very, very slowly to emphasize getting close to 0. Well, any questions or comments at all, folks, getting through this prediction here? Okay, it's a challenging problem because we're looking into net growth rates, one specific factor that determines the population size. We're getting things that aren't exactly percentages. We just know we can convert them to a percent if we wanted to using this structure right here. And then at the same time, you have to make a prediction, which means it's basically a redo of this problem, except it's in table form, not in graph form. And I recall this problem was a really challenging one when we went through it on class. So To practice this a little bit more, let's take a look into the example 4. Here we're switching up the country. We're going from the USA to Afghanistan. So completely different side of the planet. We're looking into the same base years, 1980, 1995, 2019. And we're going to do the same computations, make the same assumptions. We're assuming immigration is not a factor whatsoever to any of these net growth rates we're looking into. We're going to base our information just purely on that table. So first thing we have to do is construct the table. So let's rebuild that structure. We're going to have a year. And then in the next column, this is going to be the net growth rate. And just so that we don't have to say it 3 times, we'll just mention this part right here. We mean specifically per 1,000 people. So same years, put in 1980, 1995, and 2019. And also to emphasize, you don't have to do it as a table. As long as you put in the right information, you say which year belongs with which net growth rate, and it's easy to read what you mean, then it's completely fine to convey your information in a different way. And hey, if you like the bar graph, you can put it in as a bar graph as well, much like in this CPI problem here. So now from this on out, here's what's going on with Afghanistan. Very different place from the USA. Their birth rate per 1,000 people in 1980 is 51.8 people, many times greater than the USA. Their death rate was tragically very, very high as well, 24.1. So that's our first computation. So take 51.8 minus 24.1, and we get a net growth rate of 27.7. Then just do it all over again. From 1980 to 1995, much like US, it was pretty stable in the birth rate. For this country, Afghanistan, it actually went up by a little bit. Only difference is it's many times greater than the birth rate of the USA. So take 52.6 minus 51.8, and we get a growth rate of, oh, wrong tab, here we go. Oh, hang on, sorry, I'm not sure where I grabbed my values. 52.6 minus 20.1, so that's a massive typo there. Let me fix that. That'd be a pretty tragic death rate. 20.1 is bad enough. So minus 20.1 is 32.5. So the growth rate went up. And that's because we had good change in both directions. The birth rate increased in 1995, and the death rate decreased by even a larger amount as well. So after that, here are the weird years. And again, every time I look at information like this, I don't think this is talked about enough in the news. If you take the 2019 table for USA, and just for a moment, let's compare it against Afghanistan. In the USA, the largest economy in the whole world, our death rate is 9 in the year 2019. If in Afghanistan, it's 6. To me, that's completely shocking. And again, that's a whole nother research project to look into. There are various reasons why this is the case for 2019. It being a COVID year could be a big part of that reason as well, but I don't know if that is the biggest factor. It might have been pretty similar table if that was the year 2018 as well. We might have seen the same difference as we are seeing here, just about the same. So sorry for the sidetrack there. I think it's just interesting to think about the data when you're comparing now one country against another one. It's pretty shocking. But back to Afghanistan, one more computation. 2019 was pretty big for Afghanistan, just like it was for USA, but different reasons. The birth rate plummets. It's still really, really high at 32. But the death rate also goes down. It goes down by a gigantic amount. This is really impressive and great news for Afghanistan. Lots of good things must have happened from 1995 to 2019, which is impressive because it's a tumultuous country. It's a pretty rough landscape, but that death rate is phenomenal. 32.0 minus 6.0 gives us a value of 26 altogether. So that's their net growth rate in Afghanistan in the year 2019. And it's easy to get mixed up with these. So the unit of per 1,000 people is really critically important to this problem. When you see a 26, divide by 1,000, multiply by 100, and that says that the growth rate is 2.6%. And hey, that's a pretty much really close to our first problem in the notes. Nigeria had a growth rate of 2.5% in the year 2000. So in terms of growth rates, neglecting immigration completely, which is important, but we're going to ignore it for these problems, just to make them good homework problems. That's an interesting set of data. But what it also tells us is the story is different than the USA in another reason. It starts off at 27.7, seems to peak in 1995, and then it's stabilizing closer to the 1980 value, just slightly lower. So we're wondering, is it going to plateau at around 25%, 26%? Is it going to continue to decrease? That's what we're going to do in the next problem, make a prediction based off the limited amount of information we have on this 3-year set trend. Definitely don't want to rush through that. We're going to review this topic, maybe look at this graph again to think about this one, loop it back into the problem here. When we come back, not tomorrow, but when we come back on a week away from today, on the 22nd, after getting through exam 1 on the 20th, we'll finish off these notes, talk about this again rather than rushing through part B. Again, for tomorrow's class, the 16th, we're going to be reviewing for our 3rd exam. Well, I think, again, this is probably a good stopping point for us today. Any last questions or comments at all with where we got on the notes? Okay, let me see if I can bring this back. Oh yeah, here it is. So again, don't forget, for our next class on Thursday, we'll be doing our third review. It'll be as student directed as possible. So that means if you have questions, I want to start with your questions first. If we run out of student questions to initiate, I'll go through here, and I'm happy to take suggestions that you might have of any problems on this document or this document. My preference is version 2 only because they're new problems, but if you want to revisit a problem in version 1, that's wonderful as well. It's going to be primarily up to you, and I'll choose some problems here and there, give some advice on how to study, things to look into as well to start off class next Thursday. But have a great night, folks. Thanks for your hard work. We'll review and get through our 3rd exam review on Thursday. Take care.